In this tutorial, we aim to provide an introduction to Rutherford backscattering spectrometry in the channeling mode, elucidating its significance in the examination of single crystalline materials. Rutherford backscattering spectrometry is non-destructive analytical method using ion beam backscattering for elemental analysis of the solid samples. The principle of method is the bombardment of sample with energetic light ions which are backscattered from the surface atoms towards the detector. During the collision, projectiles partially lose their kinetic energy depending on the energy stopping powers, elemental composition of sample and projectile parameters, energy, mass. Outcome of the measurement is the energy spectrum of energetic ions, which is then used for qualitative and quantitative composition analysis, as well as for elemental depth profiling in subsurface layer up to several micrometers. RBS is measured in random direction, but if the incidence ion beam is aligned along the particular axis of the crystals, the ions will be guided in the channels formed by lattice atom string potentials. These ions cannot get close enough to the atomic nuclei to undergo large-angle Rutherford scattering. They will be subjected to small-angle screened Coulomb collisions with the maximum critical angle, and they will penetrate into the crystal. This effect is called ion channeling, and it can be applied in RBS modification in the channeling mode. The RBS in channeling mode is specifically applied for single crystal analysis, where the lattice atoms will form the long-range channels. During measurement, the crystal is tilted with respect to incident ion beam. If the ions bombard crystal in random direction, they will be backscattered towards the detector. Once the chosen crystallographic orientation is aligned with ion beam, the ions will penetrate crystal and we will observe strong reduction of yield in backscattered ions, especially in the case of perfect crystals. When the crystal is damaged or has some impurities, the disordered atoms or impurities can block the lattice channel and cause increase in backscattered yield in aligned channeling spectra. The aligned spectra of perfect crystals typically exhibit low backscattered yield, which is just several percent of backscattered yield captured in random direction. This is usually connected to the presence of native defects and random dechanneling. The aligned spectra exhibits characteristic surface peak connected to backscattering on the first atomic layer which shield underlying atoms. Crystal damage and lattice distortion will lead to the increased random dechanneling, and the point defects and impurities lead to the direct backscattering. The cumulation of point defects in narrow subsurface area will result in appearance of dechanneling peak. From the analysis of dechanneling peak, it is possible to determine the relative number of dislocated atoms and their depth distribution. The sample holder with the crystal is mounted on the goniometer, which will allows rotate with the sample at precisely defined step in two direction, in the direction of theta and phi axis. During the measurement, we will rotate with the sample in precisely defined regions, and we will gradually capture spectra backscattered yields in each defined positions. These spectra are integrated into one, which will gives us the random spectrum for chosen crystal sample. Simultaneously we will obtain 2D map of backscattered yield in connection to crystal rotation, which will provides us with the position of channeling direction. The position is then specified using the fine scan measurement with angle variation with small step. When the channeling coordinates are known, we will rotate with the crystal to align ion beam with the channeling direction, and we will capture RBS aligned spectrum. The channeling spectra can be captured only in the main channeling direction, as it is usually done for analysis of relative crystal disorder and investigation of overall crystal quality. However, we can also perform angular scan measurement, when the crystal is slightly rotated along one of the main axes and multiple spectra is recorded, fine scan. This is usually applied for study of the lattice channel deformation or dopant positioning. The first idea about the structure quality is given by determination of minimum normalized yield, which is given as ratio between integral yield in aligned and random spectrum. Usually, we are focused on particular region of interest defined by chosen energies, and the integration is done only in corresponding energy range. Knowing the minimum normalized yield of disordered crystal and perfect crystal, we can calculate the relative number of dislocated atoms in the disordered crystal. The energy of backscattered ions corresponds not only to the type of the target atom but also to the depth from which the ions are backscattered. It is possible to estimate the depth profiles of densities of displaced atoms. The densities of dislocated atoms are estimated from direct backscattering, and thus it is necessary to exclude random dechanneling first. The crystal quality reflects not only the level of dechanneling yield but also the width of the crystal channel. The crystal disorder will lead to the deformation of lattice channel, which can be monitored through the fine scan measurement. During the fine scan measurement, we record multiple spectra and we estimate the minimum normalized yield for each of them in the investigated region. In the next step, we will plot the dependence of the minimum normalized yield on the angle of rotation calculated from the center of the channel. The channel width is then evaluated as the half width of this plot estimated in half of the channel depth. The RBS in channeling mode can also offer information about preferential positioning of dopant or impurities in crystal lattice. To get information about dopant position, we compare random and aligned spectra in region corresponding to the dopant. If the dopant occupies interstitial position, it blocks lattice channel and both random and aligned spectra are overlapping. On the other side, dopant in substitutional position allows free movement of probing ions, and we will observe decrease of backscattering yield in aligned spectrum. It is possible to quantify the percentage of dopant atoms in substitutional positions by calculation of substitutional fraction. This can be done comparing the minimal normalized yield estimated for dopant RBS signal and for corresponding signal of the crystal matrix. The biggest advantage of this method is that it is considered as non-destructive method. Additionally, we have information about crystal disorder and its distribution in subsurface region. It also offers direct information about dopant position in crystal matrix. On the other side, this method can be successfully applied only for monocrystalline materials, and it is complicated to distinguish between individual defect types. Also, the positioning of dopant and impurities can be done only when the signal of dopant is separated from crystal matrix.